The objective of this lecture is to provide an approach for solving kinematics problems using rotating reference frames and to implement this approach on examples that employ various commonly used coordinate systems. This lecture will be divided into the following parts. First, a process is developed. For setting up kinematics problems. And this process is going to include identifying rotations, determining the number of reference frames that are needed, setting up coordinate systems, and applying the transport theorem. Then, using the process developed in the first part of this lecture, several examples are studied. Now, these examples include using Cartesian coordinates, cylindrical coordinates, and using spherical coordinates. Now, regardless of the problem being solved, the process developed in the first part of this lecture will be used. In particular, the number of rotations will be identified. Then, using the number of rotations, the number of reference frames required to solve the problem will be determined. For each reference frame that's needed to solve the problem, a coordinate system will be identified that is fixed in that particular reference frame. Once all the reference frames and coordinate systems have been developed, then the angular velocity of the last reference frame relative to the first reference frame will be determined. This angular velocity is the angular velocity of what's known as the observation reference frame, which is the last reference frame, relative to the base reference frame, which is the first reference frame. Using the angular velocity of the observation reference frame relative to the base reference frame, the transport theorem is then applied twice. The first time the transport theorem is applied leads to the determination of the velocity of the particle as viewed by an observer in the base reference frame. The second time the transport theorem is applied leads to the determination of the acceleration of the particle as viewed by an observer in the base reference frame. So now we are going to develop a process for setting up and solving kinematics problems. So this process is going to be developed as follows. So the first step in this process is to identify all rotations. Now, rotations in a problem come in one of two forms. Either they come as angles, and angles are typically denoted by variables like theta and phi, or they come as angular velocities, so angular velocity, or angular rate. And symbols that often denote angular velocity or angular rate are like omega as a vector, which would be an angular velocity, or just omega as a scalar, which would be an angular rate. Now, an angular rate is an angle per unit time, but an angle is actually the amount of the angle. And you have to be able to distinguish those two things, because ultimately we need angular velocity in the transport theorem. So if we're given angles, we have to take their time derivatives to be able to get angular rates. If we're already given an angular rate or an angular velocity, it's already given to us as an angle per unit time, and we don't have to take the derivative. That's the first thing that needs to be done. Now, once you've identified all rotations, the second step is to identify the number of reference frames. Now, this is really important, because if you don't get the number of reference frames correct in a problem, you will wind up not being able to solve the problem very effectively. So the general rule of thumb, now this doesn't apply in 100% of the cases, but it applies in a lot of the cases, is that the number of reference frames is equal to 1 plus the number of rotations. So if I have 2 rotations in the problem, I need 3 reference frames. If I have 3 rotations in the problem, I need 4 reference frames, and so on and so forth. Now, the number of reference frames themselves actually gives you a way to be able to characterize what each reference frame is. So this is the next step in the process, which is once we have the number of reference frames, what we have to do is we have to fix coordinate systems in each frame, and we have to look at the relative angular velocities between each of those frames. So step 3 is for each frame, we need to choose a coordinate system. And what that means is we have to choose a coordinate system that is fixed in that particular frame. It can't be fixed in any frame. It has to be fixed in that particular frame. It's really important that the coordinate system itself has to be fixed in whichever frame it is we're analyzing at that point. So if we have 3 frames, then there has to be a coordinate system that's fixed in each one of those frames. Now, once we've chosen we've chosen coordinate systems, then what we have to do is we have to develop what's called the angular velocity. Now, what angular velocity do we need to develop? And this is the important part, is that it's not just any old angular velocity, is that the last frame, which is where the last rotation ends, that's what's called the observation frame. So this is the last reference frame, is actually termed the observation frame. And the first reference frame is what's called the base reference frame. And you can call these things anything you want, but let's suppose we call the last reference frame, let's suppose we call the observation frame, we call it B, and we call the base frame, we call that A. Then these two things together means that we want omega BA. And once we have omega BA, then we can apply the transport theorem. Then we apply the transport theorem twice. And that gives us the velocity of the point as viewed by an observer in the base reference frame, and the acceleration of the point as viewed by an observer in the base reference frame. Now, this is a somewhat high-level procedure, but it gives you a way of being able to figure out all the constituent components that are needed. But there's one other thing that's really important in order to be able to apply all of this. Maybe two other things. So let's keep going, and we'll provide a little bit more detail. So we'll continue the process now to finish it up. So in these 5 steps, the thing we haven't done is we haven't figured out the position of the point that we're interested in. We need to get the position of the point, and that position has to be measured relative to a point fixed in the base reference frame, as we'll describe in the next step. So this would be a continuation of the process, and this would be step 6. So in step 6, we need to determine the position of the point P relative to O, where O is fixed in the base reference frame. This is really important. It has to be fixed in the base reference frame. And the reason is because recall that we want the velocity of point P as viewed by an observer in the base reference frame and the acceleration of P as viewed by an observer in the base reference frame. So the point relative to which we're measuring all our distances has to be fixed in the base reference frame. So this implies that O must be fixed in the base frame. So once we actually have that point, we measure all our distances from that point, and we get the position of P relative to O, and then that leads to the exact application of the transport theorem. So the exact application of the transport theorem will then look like this. Which is that the velocity of point P in A is going to equal the rate of change in frame A of the position of P relative to O, which is going to equal the rate of change in frame B of the position of P relative to O, plus the angular velocity of B in A crossed with the position of P relative to O. And then the acceleration of point P in A is going to equal the rate of change in frame A of the velocity of point P in A, which is equal to the rate of change in frame B of the velocity of point P in A, plus the angular velocity of B in A crossed with the velocity of point P in A. And those transports are applied successively. So first we take the position of P relative to O, we apply the transport theorem from frame B to frame A to get the velocity of point P in A. We take that result and we differentiate it again. We take the second rate of change, which is the rate of change of the velocity, gives us the acceleration, to get the acceleration of P in A. So it's really important that this is done in the following way, is that the transport is always done this particular way, is from B to A, where B is the observation frame and A is the base frame. Now, for the remainder of this lecture, we are going to go through in detail several examples that show how this is going to work. And the first of these examples is going to use Cartesian coordinates. The second of these examples is going to use cylindrical coordinates. And the third of these examples is going to use spherical coordinates. So we'll go through and we'll do all these examples one at a time. So let's consider this first example. In this first example, we have a disk. Draw this disk as a big circle. It's a big circular disk. And its center is at point O. And the disk rotates with an angular velocity, I'm going to call it capital omega with an underbar, relative to the ground. So here's the disk, I'm going to denote it D. Here's the ground, I'm going to denote it G. The ground or the board, whichever way you want to look at it. But now, on the disk is a little ball bearing. I'm going to call that point P. And the disk has a point that I've identified, which I'm going to call Q. Q is fixed to the disk. So this is important because I need a point fixed to the disk in this case. And the position of P relative to O is going to be measured in two components. Those two components are going to be along OQ, I'm going to call that component X, and orthogonal to the direction OQ, I'm going to call that component Y. Now the goal of this problem, so this is the objective, is to determine the velocity and acceleration of the ball bearing, which is at point P, as viewed by an observer fixed to the ground. Now, in order to be able to do this, to compute these two derivatives, I have to apply the procedure that I just developed. So the first step in this procedure is going to be to determine the number of rotations. So let's start solving this problem. So let's look at the solution to this problem. So the first step is the number of rotations. Well, the number of rotations in this case is equal to 1. So that implies the number of reference frames that are needed is equal to 2, because it's 1 plus the number of rotations. Now we have to figure out what are those reference frames and what are the coordinate systems that are fixed in those frames. So that's the next step. So these reference frames are as follows. They are the disk, which I've labeled D, and the ground, which has been labeled G. Now, of these, the last frame, which is fixed to the last rotation, is the disk. So that because the disk is equal to the last frame, that's equal to the observation frame. And G is the first frame, and that's equal to the base frame. So now I know that there are two frames. So given that there are two frames, we need coordinate systems fixed in each frame. So we need coordinate systems fixed in each frame. So the way that's going to be done is I'm going to label the last frame first. This is really important. We start with the last frame and we work our way backwards to the first frame. So I need a coordinate system that's fixed in the disk because the disk is my last frame. So the origin of this coordinate system is going to be placed at point O because O is fixed to the disk. And I'm going to put EX along OQ because O is fixed to the disk and Q is also fixed to the disk, which means the direction along OQ is also fixed to the disk. And this frame has to be fixed to the disk. And then I'm going to say EZ is going to be along omega. Because remember, omega is an angular velocity. And that angular velocity, if I curl my fingers in the direction of the rotation, which is in the plane of the rotation, my thumb points in the direction of the angular velocity, which is out of the page. So that's omega. EY completes the right-handed system, which is equal to EZ crossed with EX. So my basis is EX, EY, EZ. Now the next frame, or in this case, the base frame, so this is important, is that I'm going to say G is equal to the ground, and that is the base reference frame. That's the frame in which I'm going to compute all my rates of change. Now, again, I need a point that's fixed in the ground, but it turns out that just like O is fixed in the disk, O is also fixed in the ground because it's the center of the disk, and the center of the disk doesn't move relative to the ground. Now what I'm going to do is I'm going to define a basis. I'm going to call that basis big EX, big EY, big EZ. Now this has to be fixed in the ground, but there's a fairly straightforward way to do this. We're going to say that this basis is equal to little ex, little ey, little ez when t equals 0. What do I mean by when t equals 0? I mean when time is 0. So at time t equals 0, wherever these three basis vectors, little ex, little ey, little ez are, at that instant of time, those are the directions ex, ey, ez, and ex, ey, ez stay there while little ex, little ey, little ez start to rotate. Now, if you look back at the diagram, we now have a nice way of being able to describe the position of P relative to O. So the position of P relative to O is equal to x times little ex plus y times little ey. Now note, this position is described in terms of coordinates fixed in the observation frame. It's always going to be that way. The coordinates are always going to be fixed in the observation frame. So now we have two pieces of information. We have the angular velocity and we have the position of P relative to O. So the angular velocity that we have is the angular velocity of the disk as viewed by an observer fixed to the ground, and that's equal to omega. But omega is along EZ, so that's equal to big omega times little ez. And from this point forth, we can now apply the transport theorem, which is the next step in the process. So now we can apply the transport theorem. And the way we're going to apply the transport theorem is we're going from observation frame back to base frame. So the velocity of point P as viewed by an observer fixed to the ground is equal to the rate of change as viewed by an observer fixed to the ground of the position of P relative to O. But the position of P relative to O is expressed in coordinates fixed in the disk, and that's the frame that we started with. That's the observation frame. So this is the position of P relative to O and D plus the angular velocity of D as viewed by an observer fixed to the ground crossed with the position of P relative to O. So now let's go through and compute the velocity as viewed by an observer fixed to the ground. So we have that the following. The rate of change as viewed by an observer fixed to the disk of the position of P relative to O is equal to x dot ex plus y dot ey. Now the reason that it's the expression that I have here is because the coordinates little ex, little ey, little ez are fixed to the disk, so they don't change when I'm viewing motion relative to the disk, but the components x and y do change. So that's why the expression that you see is as given. And then the angular velocity of the disk as viewed by an observer fixed to the ground crossed with the position of P relative to O is equal to omega ez crossed with x ex plus y ey, which is equal to, well, now ez crossed with ex is ey and ez crossed with ey is minus ex. So I get omega x ey minus omega y ex. So if I add these together, I get the velocity of P as viewed by an observer fixed to the ground is equal to x dot minus omega y times ex plus y dot plus omega x times ey. Now again, notice that this velocity is viewed by an observer fixed to the ground, but it's expressed in coordinates fixed in the disk because the disk is my observation frame. It's always important to go back to the fact that everything is going to be expressed in coordinates fixed in the observation frame, and the observation frame is the disk. So next, The acceleration of point P as viewed by an observer fixed to the ground is the rate of change as viewed by an observer fixed to the ground of the velocity of point P as viewed by an observer fixed to the ground. I'm starting with the expression that I just came up with for the velocity of P as viewed by an observer fixed to the ground, and I'm taking its rate of change again. But again, look at the expression for the velocity of P as viewed by an observer fixed to the ground. It's expressed in coordinates fixed in the disk. So I'm going to transport myself from the disk to the ground. So this is d, dt, and d of the velocity of P as viewed by an observer fixed to the ground, plus the angular velocity of d in g crossed with the velocity of P as viewed by an observer fixed to the ground. Now we need to compute each of these quantities. So let's do the first one. The rate of change in the disk of the velocity of P as viewed by an observer fixed to the ground is equal to, well, let's take the derivative. Now, I never said that the angular velocity omega is constant. So everything in here has to be differentiated. So we get x double dot minus omega dot y minus omega y dot times ex. And then the second term is y double dot plus omega dot x plus omega x dot ey. Now, if I take that expression and I add it to the angular velocity of the disk in the ground crossed with the velocity of P and G, I'm going to get the acceleration. So let's go ahead and do that. So then the angular velocity of D and G crossed with the velocity of P and G is equal to omega Ez crossed with x dot minus omega y ex plus y dot plus omega x ey, which is equal to, now let's go ahead and let's take all the vector products. Ez crossed with ex is ey, and ez crossed with ey is minus ex. So I get omega times x dot minus omega y ey, and then I get minus omega times y dot plus omega x times ex. Now I have to add everything together. So therefore, we have the acceleration of point P as viewed by an observer fixed to the ground is equal to, well, I have x double dot minus omega dot y minus omega y dot ex plus y double dot plus omega dot x plus omega x dot ey. And then I have now, if I reorder the last two terms here, I've got minus omega times y dot plus omega x ex, and I've got plus omega times x dot minus omega y ey. Then, adding the ex and ey terms together gives x double dot. Now let's look. What have we got here? We have minus omega dot y. Now notice we have a minus omega y dot. We have another minus omega y dot. So I have minus 2 omega y dot. And then the last term is minus omega squared x ex. And then I have plus, now I have y double dot, and now I have plus omega dot x, and I have plus omega x dot plus omega x dot, so I have plus 2 omega x dot, and I have minus omega squared y ey. So that's the expression for the acceleration of point P as viewed by an observer fixed to the ground, expressed in coordinates fixed in the disk. So what we've found here is that we found expressions for the velocity and acceleration of the ball bearing as viewed by an observer fixed to the ground expressed in coordinates fixed to the disk. And the reason that we wind up with expressions that are in terms of coordinates fixed to the disk is because the disk is the observation frame. It's the frame in which we're making all of our observations. When we think about a camera, we're thinking about a camera that's fixed to the disk, and we're making all of our observations relative to the disk. But we want to communicate to an observer fixed to the ground what an observer fixed to the disk is seeing in such a way that we can obtain expressions for the velocity and acceleration of this point, which is this ball bearing, as viewed by an observer fixed to the ground. So that's going to be the end of this example. And this example used Cartesian coordinates. You'll notice that this was all done in Cartesian coordinates. The next example is now going to use cylindrical coordinates. It's actually going to use a two-dimensional version of cylindrical coordinates, which are polar coordinates, and we'll do that now. So now consider the following example, which is, this is example 2. And in this example, I'm going to be given information that's different from what I was given in the previous example. I have an arm, and this arm rotates relative to the ground. Again, I'll use G to denote the ground. And on this arm is a collar. You can think of it as like a little ring. And the position of the collar is measured from a point O, which is fixed on this hinge, which is fixed to the ground. And the distance to the collar from this point O is going to be R. This point here is going to be labeled P. That's the collar. And there's an angle that defines the amount of the rotation of the arm relative to the ground. So this direction, this dotted line direction here, this is fixed to the ground. And this here is an arm. Now, if you notice in this problem, we're given one rotation. But before we get to the rotations, this is what the objective of this problem will be. The objective, similar objective to what we had before, is to determine the velocity and acceleration of the collar as viewed by an observer fixed to the ground. Now again, we're going to go through the solution process in a way similar, or in a manner similar to what we did previously, which is how many rotations do we have? So the number of rotations is equal to 1. Now, given that the number of rotations is equal to 1, that implies that the number of reference frames equals 2, 1 plus the number of rotations. So now we can work with this as follows, is that I know I need 2 frames. What are those 2 frames? Well, what is rotating relative to what? So the arm rotates relative to the ground. So that implies the 2 frames are the arm, which we'll denote as A, and the ground, which is denoted as G. So now that I know that those are the 2 frames, and I have one rotation, which is this angle theta, I now can define coordinate systems that are fixed in each of these frames. So now again, we have to go backwards from the last frame to the first frame. So the observation frame which is equal to the last frame is equal to the arm, which is equal to A. The base frame, which is the first frame, is equal to the ground, which is equal to G. So I'm going to work my way backward from the last frame to the first frame. So A is equal to the arm. Now I need a coordinate system that's fixed in the arm. So I'm going to put the origin at point O, because O is fixed to the arm. It also happens to be fixed to the ground, but it's fixed to the arm too because it's the hinge point of the arm, so therefore it must be fixed to the arm. And now what I'm going to do is, because I have an angle theta, that immediately implies that I'm working with some sort of a polar or some kind of a coordinate system that's similar to that, because I have a single angle and that angle is theta. So I'm going to denote ER to be along OP. Now that direction OP, you notice, is fixed to the arm because it's along the arm. And I'm going to denote EZ to be out of the page. And I'm going to complete the right-handed system by saying E theta is equal to EZ crossed with ER. Now once I've done that, I can get the coordinates that are fixed to the ground. Now the coordinates that are fixed to the ground, the origin of the coordinate system is again going to be at point O. But now I have to define a basis. I'm going to call that basis EX, EY, EZ. And in order to sort of account for this in a somewhat natural way, I'm going to set this equal to ER, E theta, EZ, not when t equals 0, but when theta equals 0. Now, why would I do that? Well, if you look at these two coordinate systems, you'll see that the way I've defined them, EX and EY, if I make them equal to ER, E theta, EZ, when theta equals 0, then they line up. You can see that they'll line up because EZ is out of the page, and it's the same in both cases, right? So that's a nice thing. I have a common direction between these two, and that works out quite well. So now I know that I have everything that I need except for one thing. We need the angular velocity of the arm as viewed by an observer fixed to the ground. Now remember, I said before that when you're given rotations, you're either going to be given angles or you're going to be given angular rates. But in this problem, we were given an angle. So in this problem, the rotation is defined by an angle. not an angular rate. So that's the angle theta, right? So I need to use an angular rate. So in order to be able to do this with an angular rate, we have to take the rate of change. So theta dot is the angular rate. And the rotation takes place about a direction out of the page. So now we can figure out the angular velocity with all this information. So given that the angle theta measures the amount of the rotation, so the angle theta measures the amount of the rotation, while theta dot measures the rate of the rotation. And also, the direction EZ defines the axis of the rotation. So I have a magnitude and I have a direction. The magnitude is the rate and the direction is that axis. So that implies that the angular velocity of the arm as viewed by an observer fixed to the ground is equal to theta dot EZ. EZ is the direction of the rotation. Theta dot is the magnitude of the rotation, or the rate of the rotation in this case. So now we have all the information that we need except for one thing, which is the position. So finally, we need the position of P relative to O. And again, P is the point we're interested in, and O is the point from which we're measuring distances, because O is fixed in the base frame. And that is really important. It's the same thing I said before. O is fixed in the base frame. So in this case, the position of P relative to O is equal to R ER. It's a distance R in the direction ER, right? Now, ER is fixed in the observation frame. So since it's fixed in the observation frame, we need to apply the transport theorem. From A to G. So the first thing we're going to do is we need to get the velocity, and then we need to get the acceleration. So the first thing we need is we need the velocity of point P as viewed by an observer fixed to the ground. That's equal to the rate of change in the ground of the position of P relative to O, which is equal to the rate of change in the arm of the position of P relative to O, plus the angular velocity of the arm as viewed by an observer fixed to the ground crossed with the position of P relative to O. So we're going to get this rate of change first to get the velocity. So we have to compute these two terms. So then the rate of change in the arm of the position of P relative to O is equal to R dot ER. Because again, ER E theta EZ is fixed in the arm. So the only thing that's changing is that distance. So R dot ER is the rate of change of the position of P relative to O as viewed by an observer fixed to the arm. And the angular velocity of the arm as viewed by an observer fixed to the ground crossed with the position of P relative to O is equal to theta dot EZ crossed with RER, and EZ crossed with ER is E theta, so I get R theta dot E theta. from which we wind up with the velocity of point P as viewed by an observer fixed to the ground is equal to r dot ER plus r theta dot E theta. And once again, consistent with everything else, this velocity of point P as viewed by an observer fixed to the ground is expressed in coordinates fixed in the arm because the arm is the observation frame. So it's the same thing. It's the observation frame. We're always expressing our quantities in the observation frame, which is the frame that's fixed to that last rotation. So next, we can compute the acceleration of point P as viewed by an observer fixed to the ground. And that's the rate of change in the ground of the velocity of point P as viewed by an observer fixed to the ground. But again, our observation frame is the arm, so we're going to transport ourselves from the arm to the ground. And we can get all these quantities the same way we got the quantities for going from position to velocity. So the rate of change of the velocity is viewed by an observer fixed to the ground, that rate of change in the arm. Again, if we look at the last expression, which is the velocity of point P is viewed by an observer fixed in G, ER and E theta are fixed in the arm. So this gives R double dot ER plus R dot theta dot plus R theta double dot E theta. And then the angular velocity of A and G crossed with the velocity of point P in G is equal to theta dot EZ crossed with R dot ER plus R theta dot E theta, which is equal to, well, EZ crossed with ER is E theta, and EZ crossed with E theta is minus ER. So then we wind up with R dot theta dot E theta minus R theta dot squared ER, from which if we add all the terms together, we get the acceleration of point P and G is equal to R double dot minus R theta dot squared ER, and then we have plus 2 R dot theta dot plus R theta double dot E theta. Now this time when we solved the problem, we used polar coordinates, cylindrical coordinates. Polar coordinates are basically the two-dimensional version of cylindrical coordinates. Cylindrical coordinates have a z component. Polar coordinates only have an ER and an E theta component. So that's why we don't have an EZ term in this expression, because it's a two-dimensional problem. But they're the same thing except for the fact that there's a z component. But again, this gives us an example of how to use cylindrical coordinates to be able to solve for position and velocity as viewed by an observer in a base frame when that cylindrical coordinate system is rotating relative to the base frame. So now we're going to consider one more example in this lecture. And this example is going to use spherical coordinates. So in order to be able to set up this problem, we have to draw a picture first. But what we have here is we have what's called a spherical pendulum. And that spherical pendulum is one that you have a ball and socket joint, and that ball and socket joint is fixed to the ground, and point O defines the point on the end of the arm, which defines that ball and socket point. So I'm going to a ball and socket joint. So I'll call that point O. And on the other end is a point, or a little protrusion in the arm, and I'm going to call that P. Now this moves in 3 dimensions. So this problem, like I said, is a little more complicated than the problems that we did earlier. And in order to be able to define this point, I'm going to draw some some directions which are fixed to the ground. So this direction vertically is a direction from which an angle phi is measured, and that angle phi takes me to the arm. And this direction, which is off to the left and horizontal, this direction to this point here, which I'm going to call Q, which is the projection of point P into the horizontal plane. So this you can think of as being like the horizontal plane. And that horizontal plane is such that this direction that defines OQ, this angle is going to be called theta. Now, in order to make this a little bit clearer, I'm going to just define this direction here as EX, this direction off to the sort of left or southwest direction, if you want to call it that. And the direction off to the right, I'm going to call that direction EY, and I'm going to call the direction up, I'm going to call it EZ. Now, that basis, EX, EY, EZ, is going to be fixed to the ground. That'll just give me an anchor from which I can work with. I can work with everything a little bit more easily, and instead of having to make up a lot of terminology, which would probably make this problem a little more complicated. So I have two angles, theta and phi. And then the distance from O to P, I'm going to call that distance capital R. Now, that distance is actually a constant because this is it's a rigid arm. So the objective here is to determine the velocity and acceleration of the end of the arm as viewed by an observer fixed to the ground. Now, as I said, this problem is a little bit more complicated, so we have to really be careful with the way we define frames. So the first thing we have to do is we have to look and see how many rotations there are. That's where we're going to start this solution. We'll start it on the next page. So the solution is going to proceed as follows, which is how many rotations are there? So the number of rotations is equal to 2. So that implies the number of reference frames equals 3. Now, if you notice, the observation frame is going to be the frame that's fixed to the last rotation, and the last rotation takes me to the arm. So the observation frame has to be the arm. The base reference frame has to be the ground. But I somehow have to get these intermediate frames, and this is what's going to make this problem really complicated. So in order to be able to see this, let's draw this picture again. I'm going to draw it a little different from the way I drew it before, which is that here's the arm, and here's this point P. I project it down here. I get this point Q. So here's P, here's Q. Here's this angle theta, and here's the angle phi. And again, I have EX, EY, and EZ. Now, because we're going to follow spherical coordinates in this particular case, I'm going to define 3 frames. And these 3 frames are going to be as follows. First, is the observation frame, which is the last frame. Now, this one's hard to describe first, so I'm going to describe the intermediate or second frame slightly before I describe the last frame. But I'm going to kind of do them at the same time, which is if I look at the EZ OQ plane. If I look at that plane, so there's EZ, and here's this direction. I'm going to call this like OQ, if you want to call it that. you can see that point P is here, and this angle is phi. So, but in order to be able to describe OQ, that's why I'm kind of going to do this in parallel, I need a second picture which looks down on EZ, which allows me to be able to describe this direction OQ, because here's EX and here's EY. So what I'm going to do is I'm going to call this direction, if you put Q out here, I'm going to call this direction ER. And then this direction that is out of the page in this picture is EZ, which is already sitting there. And then this direction, which is the one that is EZ crossed with ER, gives me what I'm going to call E sub theta. Now, we know that EX, EY, EZ is fixed in G, because I already said that. That was earlier. So EX, EY, EZ is fixed in G. I'm going to say that ER, E theta, EZ is fixed in a frame I'm going to call A. And now what I'm going to do is, now because OQ is along ER, I can now replace OQ with just calling it ER. And I'm going to define a third frame such that this direction along OP, I'm going to call it U sub R. And then if you look, because EZ crossed with ER is E theta is into the page, I'm going to call that direction U sub theta. And then the cross product of U theta with UR, I'm going to call that direction U sub phi. So this last frame over here, which is the one that is in which this basis UR, U phi, U theta is fixed, I'm going to call that frame is going to be B. So UR, U phi, U theta is fixed in a frame I'm going to call B. Now, B is the observation frame. Because it's the one fixed to the last rotation. So I know that I have to go from B to G. So in order to be able to define these frames a little bit more carefully, I'm going to define them in the following way, which is that I'm going to say that the frame A is the EZ-OQ plane. And then I'm going to define the frame B to be the plane. If you look at it, you'll actually see that that plane rotates, and relative to the EZ-OQ plane, it's going to be the UR U theta plane, or the U theta UR plane. So let's put that on the next page. So we have the following. Reference frame A is equal to the EZ-OQ plane. And reference frame B is equal to the UR U theta plane. Now, in this case, B is the observation frame. So because I'm going to apply the transport theorem from B back to G, because G is my base frame, I now have to set up coordinate systems fixed in all these three frames. So B, which is equal to the UR U theta plane, I'm going to define the following coordinate system fixed in this frame, which is the origin is going to be at O. I'm going to define UR is along OP. And now what's really important is how I define the other basis vectors. So in this case, I'm going to define u theta to be along EZ crossed with OQ. And then u phi, because the basis is ordered UR, U phi, U theta, so I'm going to take U theta crossed with UR. Because that's 3 crossed with 1. Now the next frame is frame A. That's a little bit easier to describe because it's the EZ OQ plane. And the origin of this coordinate system is again going to be at O. And then I have all the directions defined fairly nicely, which is that I have ER, which is along OQ, and EZ is given, it's as defined, and E theta is equal to EZ crossed with ER. And just for completeness, we have a frame G, but G, I'll put it here, G is equal to the ground, and the origin is at O, and this basis EX, EY, EZ is given. That's what it gave at the beginning of the problem. So now, in order to be able to compute the angular velocity of B and G, so we need omega BG. But notice that B rotates relative to A and A rotates relative to G. So the angular velocity of B in G is equal to the angular velocity of A in G plus the angular velocity of B in A. So now we need to compute each of these angular velocities. So then, the angular velocity of A in G is equal to theta dot times EZ, and the angular velocity of B in A is equal to phi dot times U sub theta. And again, let's draw the pictures so we can see what's going on here. Here is the basis EX, EY, and then EZ is out of the page. Here's the direction ER. Here is the direction E theta. And this angle here is theta. This angle is theta. So this implies that omega AG is equal to theta dot times EZ, because, again, the amount of the rotation is theta, so the rate of the rotation is theta dot. Now, if you look at the next rotation, this direction is ER, this direction is EZ, this direction is UR, and this direction is U sub phi. And the direction into the page is U theta, which also happens to equal E theta, but I'm really interested more in U theta because I'm interested in this basis UR, U phi, U theta. So this angle is phi, this angle is phi. So that implies that the angular velocity of B and A is equal to phi dot times U sub theta. So then if we add angular velocities, so adding omega AG and omega BA, we obtain the angular velocity of B and G is equal to the angular velocity of A and G plus the angular velocity of B and A, which is equal to theta dot EZ plus phi dot times U sub theta. But we need this expressed in the coordinates fixed in the observation frame. So omega BG must be expressed in coordinates fixed in the observation frame, not any other frame. It's got to be the observation frame. So that means EZ isn't fixed in the observation frame. So as a result, we need to convert EZ to the basis UR, U phi, U theta. Now, let's go ahead and do that. If you look at the diagram, you can actually see that we'll be able to do it. We'll draw the diagram again just to reinforce everything. So now, going back to the diagram that will allow us to be able to convert EZ, here's EZ, and here's UR. Now, if this direction is U sub phi, then that implies that the direction opposite that is minus U sub phi. So since this angle here is phi, we now can get an expression for EZ in terms of UR and U phi. EZ is going to equal cosine of phi times UR minus the sine of phi times U sub phi. It's got a cosine component in the UR direction. It's got a sine component in the minus U phi direction. So now we actually have a way of being able to write the angular velocity of B in G. So we then have omega BG is equal to omega AG plus omega BA, which is equal to theta dot EZ plus phi dot U theta, which is equal to theta dot times. Now I have an expression for EZ. It's cosine of phi UR minus the sine of phi U phi plus phi dot times U sub theta, which finally gives omega BG is equal to theta dot cosine of phi UR minus theta dot sine of phi U phi plus phi dot times U sub theta. And you can see that that's in the correct order because the basis is UR, U phi, U theta, 1, 2, 3. That's the way it is. So we now have that. Now, you know, the position in this case of P relative to O, because O again is the point that's fixed in the base frame, is just equal to R times UR. That part's actually fairly straightforward because it's a distance R in the direction UR. So that part's not that bad. So let's start with all this information and let's work our way forward and apply the transport theorem twice now. So then, transcribing from the last page, the position of P relative to O is equal to R times UR, and the angular velocity of B in G is equal to theta dot cosine of phi UR minus theta dot sine of phi U phi plus phi dot times U sub theta. So now we can use these two pieces of information to compute the velocity and acceleration of the end of the pendulum arm as viewed by an observer fixed to the ground. So first, the velocity of point P as viewed by an observer fixed to the ground is the rate of change in the ground of the position of P relative to O, which is equal to the rate of change in frame B of the position of P relative to O plus the angular velocity of B in G crossed with the position of P relative to O. Now, because R is constant, that implies that r dot is equal to 0. But because r dot is 0, we then have that d dt in B of the position of P relative to O is also 0, because again, UR is fixed in frame B. So that first term just disappears. So all we need to worry about is the second term. So the angular velocity of B and G crossed with the position of P relative to O is equal to theta dot cosine of phi UR minus theta dot sine of phi U phi plus phi dot times U sub theta crossed with R UR. Now let's take the cross product. So UR crossed with UR is 0. U phi crossed with UR is 2 crossed with 1, which is minus U theta. So we get R theta dot sine of phi times U theta. And then U theta crossed with UR is U phi. So I get plus R phi dot U phi. And putting this back in the right order of the basis, we get the velocity of P in G is equal to R phi dot U sub phi plus R theta dot sine of phi U sub theta. So that gives us the velocity of point P as viewed by an observer fixed to the ground. And again, you'll notice it's expressed in coordinates fixed in the observation frame. So now we can actually use this expression to compute the acceleration of point P as viewed by an observer fixed to the ground. So next, the acceleration of point P as viewed by an observer fixed to the ground is the rate of change in the ground of the velocity of point P as viewed by an observer fixed to the ground, which is equal to the rate of change in frame B of the velocity of P as viewed by an observer fixed to the ground, plus the angular velocity of B and G crossed with the velocity of point P as viewed by an observer fixed to the ground. So the first thing we need to do is we need to compute the rate of change in frame B of the velocity of point P as viewed by an observer fixed to the ground. So let's figure out what that is. So again, recall that the coordinates UR, U phi, U theta are fixed in B. So we get R phi double dot U phi, that's the first term, plus R times theta double dot sine phi plus theta dot times phi dot times cosine of phi times U sub theta. And that's just using the product rule for differentiation, and again noting that the basis vectors UR, U phi, U theta they're fixed in frame B. So then the angular velocity of B and G crossed with the velocity of P and G is equal to, we've got theta dot cosine of phi UR minus theta dot sine of phi U phi plus phi dot U theta crossed with R phi dot U phi plus R theta dot sine of phi times U theta. So now we can take the cross products, and we have UR crossed with U phi as U theta. So we get R theta dot phi dot cosine of phi times U theta. UR crossed with U theta is minus U phi. So we get minus R theta dot squared cosine of phi sine of phi times U phi. And then U phi crossed with U phi is 0. U phi crossed with U theta is UR. So we get minus R theta dot squared sine squared phi times UR. And then the last term is minus r phi dot squared times ur, because u theta crossed with u theta is 0. U theta crossed with u phi is minus ur. So now I can add these terms together to get the acceleration of point P in G. And again, if I look at all the UR terms, I've only got one. I've got minus R phi dot squared UR. And now let's look at the U phi terms. The U phi terms, I've got an R phi double dot. That's the first term. And then the other U phi term I've got is minus R theta dot squared cosine of phi sine of phi times u phi. And then the last term is all these terms that involve u theta. So those are the longest ones. I've got an r theta double dot times the sine of phi. And then if you notice, I have an r theta dot phi dot cosine phi. I have another r theta dot phi dot cosine phi. So that gives me 2r theta dot phi dot cosine of phi. And that's all the terms that involve u theta. So there's the u theta term. And that's the acceleration. So again, you see that when we do all these problems, we work our way from the last frame back to the first frame. The frames are not necessarily always that easy to figure out. This problem, we had some tough frames to figure out because the whole construct of the frames was not given by nicely defined objects. We had to actually define planes. But I want to spend a little bit of time doing this again, just so that you can see what these frames are a little bit more clearly if it wasn't that easy to do so previously. So let's take a minute to do that now. So let's examine these frames a little bit more. So I'm going to look at this big picture again, and it might help actually figure out these frames. So here's EX, here's EY, and here's EZ. So this first rotation, if you notice, because here's the position, there's P up there. Now, when you put Q down here, you'll notice that the first thing that comes that becomes maybe a little bit evident, well, it's not necessarily completely evident, is that if I was to take this plane, here's this plane. That plane that's the EZOQ plane. So that's my first frame. It's like a door, if you want to think of that. That door is kind of opening. Now, the next frame, which is the one that is a little bit less easy to see, if you want to call it that, is that, see this direction right here. I'm going to draw it out a little bit this way. That direction is, because this direction here is ER, that direction is E theta, which is also U sub theta. So the second frame is this, if you want to think of it, another door. There's another door. It's like a parallelogram. And it's this plane right here. And that's the second frame. So the first frame, which is this one right here, this is the EZOQ plane. This next one, because this direction right here is UR, and that direction is E theta, this frame right here is the UR U theta plane. So in this case, we have the following, which is the EZOQ plane rotates relative to the ground. And I can call this A. And B, which is equal to the u theta plane, rotates relative to A. And hence I get that the angular velocity of B and G is equal to the angular velocity of A and G plus the angular velocity of B and A, which is equal to theta dot Ez plus phi dot times u theta. And that's really important because you have to identify how these rotations take place. And if you can't figure out the rotations, then it's very difficult to figure out anything else. So that takes us to the end of this example. Now we've done 3 examples in a lot of detail. And we can summarize this lecture as follows. So to summarize, we first developed a process for setting up a kinematics problem. And that process involved determining the number of rotations. So we had to identify the rotations. And then we had to figure out the number of reference frames. And then we had to fix coordinate systems in each frame. And then we had to determine the angular velocity of the observation frame relative to the base frame. And then we applied the transport theorem. And then using this procedure, we studied 3 examples in detail. And those examples used Cartesian coordinates. That was the first example. Second example used cylindrical coordinates. We actually used a 2-dimensional version of cylindrical coordinates, which were really polar coordinates. And the third example used spherical coordinates. And we use this procedure in part 1 to do everything for all of these different examples. We went through and we applied that procedure 3 times to be able to do these 3 problems. So that takes us pretty much to the end of this this lecture, and we'll continue on with the study of various aspects of dynamics and kinematics as we move through other lectures.